In this video, I will go over the homework that follows the lecture 14.2 that focuses on the trapezoidal approximation. And as always, I hope that you watched all the lectures. And let's go ahead and start the homework. The first question is asking us for a given graph to use trapezoidal approximation with n equals 3. So let me copy this picture and bring it into my whiteboard over here. And let me figure out how to zoom in here. There you go. And let's just follow the instructions. A is equal to 0, so we start here. We go up to 3, so we go up to here. And n is equal to 3, so if a is 0, b is 3, and n is 3, then delta x can be found using this formula. And in this case, 3 minus 0 over 3 is just 1. So we can create this partition x0, x1, x2, and x3. And now to find T3, we are going to find the areas of this trapezoid. But what we learned in the lecture is that it's not necessary for us to really think of it as areas of trapezoids. We can just use the fact that trapezoids are the area of each trapezoid is half of the area of the rectangle founded on each of its bases. So in other words, the formula for T3 is this. We're going to have delta x over 2, and here we're going to have f of x0 plus f of x1. Rather, we're going to have 2f of x1 plus 2f of x2 plus f of x3. So this is the formula. This is what we learned from the lecture. And to actually compute it, we need to have all the ingredients. So here we have delta x is 1, f of x0 is 5, f of x1 is 8, f of x2 is 3, and f of x3 is 4. And here's what we get. 5 plus 16 plus 6 plus 4. So we have 21, 31. 31 over 2 is just 15.5, whatever units squared there are. So let's enter this. And we got the first problem correct. Here we are asked to do pretty much the same task. However, the graph is not given, and if we need to see something, we may graph it ourselves. But in terms of setting up the problem, we don't really need to have the actual graph. We can just use any line just to understand the relations. And we're looking for T4, so A is equal to 0, B is equal to 4, N is 4, so delta X will be B minus A over N. It's also going to be 1. Now to set up the partition, again, I don't need the graph itself, but I do kind of want to see the x-axis. So if A is 0 and B is 4, and we have 4 rectangles, then this is your partition. This is x0, x1, x2, x3, and x4. And we're setting up T4. So T4 will be half of delta x times f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus f of x4. Now, if you want, you can do this by hand, but we pretty much are at the step where we need to evaluate the given function at 0, 1, 2, 3, and 4. And this is the step that if you really insist on doing it by hand, you can. I, however, would like to... Well, there are two things we can do it. Two ways we can use Desmos here. We can just use tables of inputs, outputs. So here's my x, here's my f of x. Actually, I don't know if it likes it this way. So let's define the function separately. And here we can just use this functionality of Desmos to compute all the values. So we need x when x equals 0, when x equals 1, 2, 3, 4, and 5. We actually don't need 5. And then we can just plug it in and do it by hand. So we have delta x is 1 over 2, f of x0 is 0, plus 2 times 1, plus 2 times 3, plus 2 times 5.4, plus 8. And we have 1/2, 2 plus 6 plus 10.8 plus 8. So we have 26.8. So the answer is 13.4. However, you can also use Desmos in a more involved way. You can literally just plug in delta x and set up this expression in Desmos. So f of 0 plus 2f of 1 plus 2f of 2 plus 2f of 3 and plus f of 4, and the answer is 13.4. So let's go ahead and enter the answer. One way or another, you should be focusing on understanding the process rather than getting lost in the computation. So let's move on to the next problem. This is interactive one. So here we have A is -2, B is 1, N is 3. So delta x is B minus A over N. So it's going to be 1 minus -2 over 3, which is 1. And the partition will be, so basically we just need to add delta x to A until we reach B. So when delta x is 1, it's just as easy as adding 1. So we have, this is my partition and these are my 3 subintervals. And let's go ahead and play with this graph. So we're going to have it started at -2. It's going to go all the way to 1. We have fewer trapezoids right here. And we just need to drop these points on the graph. And that looks good. Let's go to the next problem. F of x is 3x squared minus x. A is 1, b is 4, n is 3. So delta x is b minus a over n. So 4 minus 1, 3 over 3. That's 1. Next, we're going to draw the partition. So we have from 1, we're going to go to 2, to 3, to 4. And this is going to be my x0, x1, x2, x3. And t3 will be delta x over 2, f of x0 plus 2, f of x1 plus 2, f of x2 plus f of x3, and I'm going to use Desmos. So I'm just going to introduce my function, 3x squared minus x. Here we have interval from 1, 2, 3, and 4. And here we're just going to adopt this formula for the case when n is equal to 3. And it looks like we got the answer, 24. Oh my god, I did not adopt the formula correctly. The answer is 57. And that's correct. All right, so the next question is about the upper bound, and let's extract the information. So a is 0, b is 1, n is 2, and in upper bound problems we need to know k, where k is the upper bound of the second derivative, and we don't know what it is. But just to give you an idea where this desire for this value come from, it's from this lecture. We have the formula right probably over here, maybe. Okay, so the upper bound for the error in trapezoidal approach is given by this formula. And it is very similar to the one we used for the midpoint approximation. And k it also represents the same exact thing. K is the upper bound for the second derivative. So we need to find the second derivative. And the first derivative is 4 times e to the 2x. And the second derivative is 8 times e to the 2x. And we are on the interval from 0 to 1. And I know that on this interval, this function is monotonely increasing. So that means it will be reaching its minimum at 0 and maximum at 1. So if I want to find k as the upper bound of the second derivative, I can just set it equal to the second derivative evaluated at 1. So it's going to be 8e squared, which is not a small number, but it doesn't matter. So now that we have all the ingredients, we can plug in these numbers into this formula. And let the Desmos do all the work. So it's going to be 8e squared 1 minus 0 cubed, which is just 1, 12 times 2 squared. So it looks like the error is 1.2315, which if we have to run to 2 decimal places is only 1.23. So that means if we use a trapezoidal approach with n equals 2, we're going to be within 1.23 squared unit of the correct answer. So, which could be a useful information. We have another very similar problem. A is -2, B is 1, N is 2, K we don't know, but we're about to find out. Function, unfortunately it's the same function. So finding its derivative is easy. Finding its second derivative is also easy. We can also, just like before, acknowledge that it's a monotone function. So on the left, whatever that left boundary is, it's going to be the minimum. And on the right, it's going to obtain its maximum. So it does make sense to set k to be equal to the second derivative at 1, which is 8e squared. And now we can plug in all the ingredients into the formula to obtain the upper bound for the error. It's going to be 8e squared 1 minus -2 cubed divided by 12n squared. Can just reuse the same Desmos calculator and replace 0 with -2. And the answer is pretty big. But the value of, maybe not this particular one, but large is a relative term in this case. 33 could be large if your overall value is 50, but 33 is not large if your area is 1000 of something. All right, so we're ready to advance to the next question. And we are looking for the error of T4 So again, the correct notation here is we use T4 to approximate this. And let's identify all the ingredients. A is 0, B is 1, N is 4. We need to find K. To find K, we're going to find the upper bound of the second derivative. So the first derivative is this. The second derivative is this. And once again, we have a monotone function that obtains its minimum on one side of the interval and its maximum on the other side. So it does make sense to set K to be equal to the output of the second derivative at 1. So it's once again 8e squared. And the upper bound for the error in trapezoidal approach here will be found using this formula. So can use the same Desmos calculator. And because n has increased, the error has decreased. So approximately it will be 0.31. We have another problem. A is -1, B is 1, N is 3. We need to find K. To find K, we consider the function and find its first derivative, then the second derivative. Then we acknowledge that it's a monotone function. So it obtains its minimum at -1, and it obtains its maximum at 1. So it doesn't get any larger than its value at 1. So it does make sense to set K equal to 2e. And now finding the upper bound for the error, we just use this formula. And once again, I'm going to delegate this task to Desmos. And the answer that we get is 0.4027. And if we had to round, it's 0.40. And it seems like we achieved 100% mastery here. And if you have any questions, feel free to reach out.